Hello everyone, I am Siddharthan. Currently, we are in the seventh module of our hands-on machine learning course, and this seventh module is all about building machine learning models from scratch. So the first model that we worked on was a linear regression model, and now we are currently working on a logistic regression model. In my previous videos, I have explained you what is the intuition and math behind a logistic regression model, and in today's video, we are going to discuss how we can find the loss function and cost function for a logistic regression model, and this is the agenda for today's video. So let's get started right away. So as I told you in my previous video, I have explained you what is meant by this logistic regression, where we will use it, and so on. I'll just give you a quick recap about this logistic regression model. So if you plot a logistic regression function, you will get a curve like this, and we call this curve as a sigmoid curve or a S-shaped curve because of this particular shape. Okay. So in this curve, we will if you see this graph, we will take Z values in the x-axis and y cap values in the y-axis. So if you notice the values on the y-axis, you can see that this y cap value lies between 0 and 1. Okay, so your y cap value cannot exceed 1 and your y cap value cannot decrease beyond 0, whereas your z value can have negative values all the way up to positive values. So it can have any values, but y cap values will lie between 0 and 1. And how we will find this y cap value is by using a sigmoid function. So this is called as a sigmoid function or a sigmoid equation. So it is given by y cap is equal to 1 divided by 1 plus e power minus z. So this is called as the sigmoid equation, and now we need to know what is meant by this z. So this z is nothing but z is equal to wx plus b. So if you just look into this equation closely, you can realize this is nothing but the equation of a straight line, right? We know that the equation of a straight line is y is equal to mx plus c. Similarly, this is wx plus b, where w represents the weight and b represents the bias. So we have already discussed about what is meant by weights and bias in the previous videos. If you are not sure about these terms, I'll give the link of the weights and bias video in this video description. You can check that out. Okay. So hence we can understand that z is equal to wx plus b, and y cap is given by this particular equation, where y cap depends on the z value, and we know what is the z value. So whenever you substitute the value of z in this equation, your y cap value will lie in this range. Now we need to understand what is the significance of this y cap and why we are using this logistic regression. Okay, so these are the terms that we have used in this equation. So y cap is the probability that y is equal to 1. So in logistic regression, the problems we work on will be a binary classification problem. Binary classification in the sense we will try to classify the data points as two classes. It can be either 0 or 1, or it can be like predicting whether a news is real or fake. So in all of these cases, there are only two classes or two types. So we will try to classify our data points into these two classes, and generally we give labels to our data points. Let's say that we are predicting whether a news is real or fake. Let's say that if a news is fake, we can take that y is equal to 1. If a news is real, then we can say that y is equal to 0. So now we have two classes and we have two label values, which are 0 and 1. And now we need to find whether a news is real or fake. In other words, we will try to find whether the y value is equal to 1 or 0. So this is where y cap is useful. So what we will do using logistic regression is we will try to find the probability. What is the probability that y is equal to 1? So now look at this values. Let's say that you get a y cap value of 0.8 using this particular equation. So 0.8 basically means that you have a probability of 0.8 that y is equal to 1. So how you can say in other words is that there is a 80% chance that y is equal to 1. So what y is equal to 1 is nothing but the news is fake, right? So we can say that there is a 80% chance that the news is fake. Or if you get the y cap value of 0.2, that means there is only a 20% chance that the news is fake. So you can say that it is most probably it is a real news. So this is how logistic regression works. It tries to classify binary values. So this is why we use it in a binary classification problem, where we will try to find the whether y is equal to 1 or 0, and we won't find it precisely. So we won't calculate y is equal to 1 or 0, but we will try to find the likelihood or the probability that y is equal to 1. So that is given by the sigmoid equation y cap. Okay, so in other words of reading this probability that y is equal to 1 is, you can write this particular line like this. So y cap is equal to p of y is equal to 1x. So how you can read this line is y cap is equal to the probability that y is equal to 1 for a given value of x. Now what is meant by this x? So x is our input feature. So let's try to understand this with another example. So whenever you are training your machine learning model, you need to give it features. Let's say that we are predicting whether a person has diabetes or not. In that case, we need to train our model with features like what is the blood glucose level of a person, what is the BMI of a person, what is their weight, and so on. So all these are called as input features. So once we feed these input features and train our machine learning model, whenever you are giving new values, it can predict whether that person has diabetes or not. So X will be our input features, and this is what this Z is equal to WX plus B represents. So this X is our input feature, and W will be our weights, and B will be our bias. So if you consider a linear regression problem, so weight is similar to the slope of the line, and B bias is similar to the intercept of the line. So if you have watched my videos on linear regression, you will understand all these topics. So if you haven't, please watch those videos as well. Okay. And now the other thing which you need to remember is that the number of weights is equal to the number of input features that you have. Let's say you have 10 input features. In that case, you will have 10 different weights for each of these input feature, whereas you will have only one bias value. So bias is a one real number value, but you can consider these weights as an array. So this is all about logistic regression, where we can say that our model will try to find what is the probability that y is equal to 1. And it is mainly used in binary classification problem, and we know that the y cap value lies between 0 and 1 because it is a probability value, and probability value can lie only between 0 and 1, and this is the sigmoid equation, and this is the equation of Z. And I hope you are clear up to this point. Now the reason for let's try to understand why we need to understand about loss function and cost function for a logistic regression model. So it is quite different from the loss function that we will use for a linear regression. So we won't be using the same loss function equation that we have used in linear regression, but we need to use a different one. Let's try to understand what is the significance of this loss function. If you look at this equation, Z is equal to W X plus B. This W and B are called as the model parameters. So model parameters of this logistic regression model. Now, our machine learning model will try to find the optimum value for weight and bias, W and B. It will try to find what will be the best value for weight and bias, so that it can accurately predict the y cap value. Okay. So if your weight value and bias value are not proper, they are not optimum, then you won't get proper y cap value. So what happens in that case when you don't have proper weight value and bias value is that if your news is real, your machine learning model may predict that that particular news is fake. So it may predict wrongly. So that that is what happens when you have improper weight value and bias value. So our machine learning model will try to find the best value for weight and bias, and this is not a single step process, and it will take in multiple steps. And this is where we use an algorithm or a method called as gradient descent. So in the next video I'll explain you how we will use this gradient descent. But for now, in order to calculate this gradient descent, loss function is very important. Okay, so in order to find which parameters W and B are important, like which parameters are optimum, we need to find the loss function of the model. So and other thing you need to remember is that the weight and bias value changes in each case. So you won't get the same weight value and bias value in all the projects that you work on. So these values differ based on the data set that we have. Okay, and these values, we don't manually give these values to the model. So these values will be determined by our model by learning from the data set that we have. So we need to find which is the optimum value. Now let's discuss what is the importance of loss function and how does it influence this weight value and bias value. So loss function measures how far an estimated value is from its true value. So if you just look at this particular statement, we have two values here. One is the estimated value and the another one is the true value. Estimated value is the value predicted by our model, which is represented by this yi cap, and the true value is the true value given in the data set. Okay, so this is the actual value. So we have two values. One is the predicted value, which is predicted by our model, and the another one is true value or the actual value. And this loss function is nothing but what is the difference between these two values, the estimated value and the true value. If the difference between the true value and the estimated value is very high, that means our model is not working fine, right? Because let's say that we are predicting the salary of a person based on their years of work experience, and the true value of the salary of a person is, let's say it's about 50,000 rupees per month, and let's say our model has predicted their salary as 30,000 per month. Now there is a huge difference between the true value and estimated value, right? So the difference is about 20,000 rupees, and the difference is too huge. So you don't want that much difference between the estimated value and the true value, and that is represented by this loss function. So what is the difference or the distance between the true value and the estimated value, and this is given by the loss function. So this is the kind of loss function we will generally use in regression problems, like regression models like linear regression, where we will try to predict a particular value. So if you think about the salary example, we are trying to predict some numerical value, which is the salary. But in the case of logistic regression, as I've told you before, we will try to predict whether y is equal to 1 or 0. So we cannot use this kind of a loss function. So we need a different kind of a loss function. Okay, but the loss function definition remains the same. It is just to measure how far the estimated value and the true value are. So we cannot use this kind of loss function. And if you use the same loss function which we have used for linear regression, so if you remember, we have used this loss function for our linear regression model, and if you use this kind of loss function, your gradient descent won't work properly. So you will get a gradient descent curve something like this, and we call these as a curve with multiple local minima. Okay, so gradient descent with local minima, and we know that we generally take loss function or cost function. So I'll explain you what is the difference between loss function and cost function in the upcoming slide. But just for now, remember that in the y-axis we will take a loss function or the cost function, and in the x-axis we will take weight value and bias value. So we will try to find what is the loss function value for different parameters. So we will keep on changing the weight value and bias value, and we will try to see for which parameter value the loss function is very less. So we know that if the loss function value is less, then that means our model is working accurate, right? So we need to have minimum loss function. So we will try to see for which parameter. So this is the different parameters that we have took on x-axis. So for different parameters, we will try to take the loss function value. And if you look at this curve, there are multiple minima. So these points are called as minima, and these are called as local minima. But how does an optimum gradient descent model looks like is like this? Okay, so you will have this kind of a curve is called as a convex curve, and convex curve are really important for us in gradient descent. So then only you can reach this global minimum. So global minimum is the point. So at this point, if you just come to this x-axis, you will have some parameter values. So your parameters will be some things. Okay, so the weight value and bias value, for this particular weight value and bias value, your loss function value will be very small. Whereas if you take the weight value and bias value, let's say that we are taking initial weights. Okay, so let's take at this point, and we are taking the weights and bias value in this particular point. And if you just come to this y-axis, you can see that the loss function value is very high. So wherever you start your initial weight, we need to reach this global minimum, and it is the point for this weight value and bias value or the parameter value, your loss function will be very minimum. And for this particular action, we need a convex curve like this. You cannot have multiple minima, but you just need one single global minimum. So this is the problem with using this kind of a loss function, because logistic regression is not a convex function like but if you take the log of this loss, you will get this kind of a convex curve. So you will understand what I'm trying to say. Just hang in there. So this is the reason we are not using this particular loss function, because of the problem of local minima. Now, for this particular purpose, we need to use a different kind of loss function, not this particular equation, but we need a different loss function. And now let's try to discuss that particular loss function. So this loss function for logistic regression, we can use a loss function called as binary cross entropy loss function, and it is also called as log loss. So we are going to take log of the loss function, and the equation will look something like loss function of y comma y cap. So we know that loss function is the difference between estimated value and true value, right? Where your y will be the true value and y cap will be your estimated value or the predicted value. So loss function is the function of the true value and estimated value. So you can write the loss function as L of y comma y cap, and L of y comma y cap is equal to minus y log y cap plus 1 minus y log of 1 minus y cap. So this is the log loss equation or the binary cross entropy loss function. So this is a very important loss function formula, and you need to take note of this. And if you see this closely, you have two terms in this equation, y log y cap, and this is the first term that we have, and the second term is 1 minus y into log of 1 minus y cap. Okay, and this negative sign is common for both these terms. So this is a very important equation, and I'm not going to go detail into how we derived this particular loss function. So you can just search on internet if you want that, but we don't have to go into that much detail in this case. Okay, so this is the loss function that we have. Now we need to find out will be the loss function value. So we have already discussed that we need a very minimum loss function, and if we have a very minimum loss function, that means our weight and bias value are working fine. Right, now let's see how this loss function works. So we know that we can have only two values for y. One is 1 and 0, right? So we have this is a binary classification problem, so hence you can have only two labels, either 0 or 1. And now we are going to put the two values. So we are going to try when y is equal to 1 and y is equal to 0, and we know that y cap value lies between 0 and 1, right? So I have explained this in the first slide. So y cap value lies between 0 and 1 because it is the probability, and we get this by the sigmoid equation. So I hope you understand this part. So if you just look at this equation, your y can take the values of either 1 or 0, and your y cap can take any value between 0 and 1. So this is how your equation is. And now what we will do is, let's try to substitute the value of y is equal to 1 and then y is equal to 0. So let's do that separately. Now we are going to give y is equal to 1. Let's say that a news is fake, and for fake news we are going to give the label as 1. So what happens is, in this case, if you substitute the value of y is equal to 1 in this equation, so this will be 1 into log y cap, and this will be 1 minus y will become 1 minus 1, right? And this particular part becomes 0 now. So 1 minus 1, and because of this particular term, the second term will become 0, and you will have only this first term, which is log y cap. So 1 into log y cap, which is equal to log y cap. So that's what I have written here. So L of 1 comma y, whenever that y value is equal to 1, your loss function will be minus log of y cap. Okay, so this will be our log value. So I'll just remove this orange. Okay, so now, so we have two terms, and whenever y value is equal to 1, this second term will be 0, and you will have only this term, and this y value is equal to 1. So you will get a loss function of 1 comma y cap is equal to minus log y cap. And whenever y value is equal to 0, we need to discuss that as well. So whenever y is equal to 0, if you substitute the value of y as 0, you will get L of 0 comma y cap. Now this particular term will become 0 because we are substituting y is equal to 0. Therefore this term, because of 0 into log y, so 0 into any number is 0, so this particular equation will become 0. And now 1 minus 0, so we are substituting y is equal to 0, so therefore this 1 minus 0 will be 1. Okay, so this is the second term. Now you will have this first term will be 0, and you will have only this second term, which is negative log of 1 minus y cap. So this negative sign comes from here. So as I've told you, this negative sign is common for both first term and the second term. So this is the loss function you will get whenever y value is equal to 1 and y value is equal to y cap. Now let's try to understand what is the significance of this. So why we need this kind of a loss function value. So our goal, so I'll just remove this just a second. So our goal is to have a minimum loss function value, right? So as I've told you, minimum loss function means there is not much difference between the true value and the estimated value. So we always want a minimum loss function. And now we need to understand when this loss function value will be minimum. Just look at this term minus log y cap. For what value of y cap your loss function will be minimum, and in this case, for what value of 1 minus y cap your loss function will be minimum. So that is the important inference that you need to get in this case. So we always want a smaller loss function because that means our model is working accurately, right? So we always want a smaller loss function, hence y cap should be very large, so that negative log y cap will be a large negative number. So large negative number means it is a very small number, right? So large positive number is a large number and a large negative number is a very small number, and we know that it is basic math. And if you want a very large negative number for loss function, this log y cap value should be very huge. For log y cap value should be huge, this y cap value should be very large. So that's what I have mentioned here. So if you want a smaller loss function, your y cap value should be very large, and if your y cap value is very large, this minus log y cap will become a very large negative number, which means your loss function value is very minimum. It is a very small number, and we know that our y cap value can lie only between 0 and 1. So whenever I'm saying that a y cap value should be very large, it is nothing but it is closer to 1. And whenever in the case of y is equal to 0, we always again want a smaller loss function. In this case, the y cap value should be very small. So when the y cap value should be very small, your 1 minus y cap value will be large, and your negative log 1 minus y cap will be a large negative number. So this is just opposite to it. So this is log of y cap, but this is 1 minus y cap. So it is just quite opposite to it. because if you have a larger number, so a number close to 1 for y cap, the difference between 1 minus y cap will be very small. So let's say that you are having the y cap value of 0.9, so 1 minus 0.9 is 0.1, and if you have log of 0.1, it is a very small number, so we don't want that. So whenever y is equal to 1, we want the y cap value should be large, which is closer to 0, and whenever y is equal to 0, you want your y cap value should be very small. I'll just show you how this what this basically means. Let's try to take different value for y cap for this equation and y cap for this second equation. So first is negative log of y cap. So I'll just go to my Google Chrome, so you can just type in scientific calculator where you can just calculate some basic values. So I'll just give negative log of some number. So we know that for y is equal to 1, we want a very large y cap value. So what I'm going to do is a large y cap value, in the sense it should lie between 0 and 1, so the large number should be very closer to 1. So I'll just give 0.9. okay, so if you give 0.9, your loss function value is 0.045. so this negative log of y cap is nothing but our loss function, right? So loss function is equal to minus log of y cap, and if you see here, if you take a larger number like 0.9, you get a very small loss function value, which is 0.045 and so on. Now what we are going to do is, we are going to take a very small number. So we are going to take this equation and we are going to take a very small number, and now we are going to check the loss function value. So negative log of smaller value, in the sense which is closer to 0. So I'm taking 0.1. So in this case, your loss function value will be 1. So 1 is a very huge number, right, when compared to the 0.04. So previously we have calculated the log, like negative log of 0.9. So 0.9 is a larger number than 0.1. So whenever you are taking the y cap value, so this 0.9 and 0.1 represents y cap value. So whenever you are taking a larger y cap value, your loss function will be minimum in this case, and whenever you are taking a small number, your y cap value will be very large. Okay, so you can compare these two numbers. Now this is what I have mentioned in this particular inference part. So these two lines are the inference that we get from this particular equation. So when y is equal to 1, you will get the loss function equation like this, and for this equation y cap value should be very large, so that it will be a large negative number and so on. Now the thing is, uh, as I've told you, for loss function to be minimum, y cap value should be very large, that it is closer to 1, which is similar to y is equal to 1. So this is what the loss function will try to do. So whenever your y value is equal to 1, it will try to push the y cap value to 1 as well. Whereas whenever your y value is equal to 0, it will try to push the y value to 0 as well, y cap value to 0 as well. Now let's see. Now we have negative log of 1 minus y cap, and let's try the similar part here. So I'm taking negative log of 1 minus y cap. 1 minus y cap. So we need a very small value in this case. So it's just opposite to it. So whenever you take a very small value, your loss function value should be minimum. And when you take a larger value, which is closer to 1, your loss function value should be large. So let's try that. So I'm taking a very small value like 0.1, which is closer to 0. So if you will get a value something close to this, 0.045. But when you take the log value, the y cap value is negative log of 1 minus y cap, and now I'm going to take a larger number like 0.9. So in this case, you will get the loss function value as 1, which is very large. So these two are just opposite to it. So as you can see here, so these two cases are just opposite to it. So whenever your y value is equal to 1, your loss function will be minimum, and it will try to push your y cap value to 1, and whenever your y value is equal to 0, your loss function value will try to push your value to 0. So this is what happens in a loss function case, and we will try to use that in the gradient descent. And now we need to understand what is the difference between this loss function and cost function. So this is a very important part. A lot of people may still have ambiguity on what is meant by this loss function and cost function, and I think I have mentioned in one of the videos as well. So what is the difference between them? But I'll just try to explain this to you again. So if you think about loss function, we will try to find the difference between the true value and the predicted value for only one case, for only one data point. So let's say that there is a person and he makes a salary of about 50,000 rupees, and the machine learning model had predicted the salary of the person as 30,000 rupees, and now we try to find the difference between the true value and the estimated value. And now we are doing this for only one data point, right? So whenever you do the difference, you do the estimation of the difference between the true value and the predicted value for one data point, it is called as loss function. And the cost function is something when you do the same thing, when you try to find the difference between the true value and the predicted value for the entire data set, it is called as the cost function. So that is the difference between them. It is basically very simple, right? So loss function mainly applies for a single training set as compared to the cost function, which deals with the penalty for a number of training set or the complete batch. So the basic things of loss function and cost function are basically the same thing. They try to find the difference between the predicted value and the true value, but loss function is concerned with only one value, whereas cost function is concerned with all the values or all the data points in a data set. So that is the difference between them, and this is a very important point, and you may be asked for this particular question in your interviews related to machine learning as well. So please remember these point, or you can take a note of it as well. Now there is a quite change in this loss function and cost function, okay, because of the difference in their definitions and their understanding. So your cost function will be slightly different from this loss function. So let's try to understand how the cost function looks like. So we know that this is the loss function equation, which is L of y comma y cap is equal to minus y of log y cap plus 1 minus y log of 1 minus y cap. And now what we need to do is, for cost function, we need to take the summation of all the loss functions of all the data points that we have in a data set. So it is actually the same equation. You just need to take the summation of all the data points and you need to divide it by the total number of data points. So let's say that M denotes the number of data points in the training set. Let's say that we have about 100 data points in a data set. So we have salary data for 100 different people in a data set, and M denotes the number of data points that we have. Okay, so that is the importance of M, and your cost function equation will look something like this. So this equation may look very big and long, but it is actually very simple. This is basically the same equation. You just need to include the summation and this average. So we are just taking the average of all the loss function. Okay, so this cost function is represented by j of w comma b, whereas loss function is represented by L. So w and b are nothing but weight and bias value. So we always represent cost function as a function of weight and bias value, because like your cost function value changes depending on the weight value and the bias value that you have, as I have told you in the gradient descent part. Okay, so as you can see here, so for different weight value and bias value, your cost function value will change. So we always represent our cost function as the function of weight and bias. Okay, so that's why I've represented it as j of w comma b, and j of w comma b is equal to 1 by m, where m denotes the total number of data points, summation of all the loss functions. So how we will find the cost function is, our machine learning model will try to find the loss function for all the individual data points. So once it tries to find the loss function of all the data points, it will take the average of it. So it will try to sum it up and take the average of it, and it is called as the cost function. Okay, so it is cost function is nothing but the mean average of loss function, so nothing more than that. So if you have 1,000 data points in a data set, so your model will try to find the loss function for all these 1,000 data points, and once it found the loss function of all these data points individually, it will try to take the average of it, and that average is called as the cost function. So that is the simplest definition I can give you. So j of w comma b is equal to 1 by m summation of L of y comma y cap. So you can just represent this as I just missed it here, so you can just write it as m. So let's say this is m and I is equal to 1. So this is how we represent summation, right? So 1. So similarly you can do the same thing here as well. So at the top of the summation we represent the total number of values you have, and I is equal to 1. So I is equal to 1. So this should come on top and below the summation part. So everyone knows this. Okay. So summation of loss function of yi and yi cap. So yi is nothing but all the individual values. So we are trying to take the summation of all the individual values. So this equation basically remains the same. The only difference is we will try to find the values for all the different data points and take and sum it up. So that's the difference. So it will be is equal to minus 1 by m. So this minus comes from here. So 1 by m, where m denotes the total number of data points, summation of m and I is equal to 1. So yi, which is represented by this. So y log y cap will become yi log y cap I plus 1 minus y will be 1 minus yi cap log of 1 minus yi cap. So these two equations are basically the same. They are actually similar. We just need to sum it up. So that's the difference, and we will do this for all the data points individually. So that's why we are represented I here. So I is nothing but the individual data points. So individual data points that we are taking from the start to the end of all the data points that we have in a data set. Okay, so this is how the cost function looks like in a logistic regression model. So this is a very important important for us. So you can take note of this cost function equation and loss function equation, because we are going to use these equations in our logistic regression model. So while we are building our logistic regression model from scratch in Python, we need to build the gradient descent for the logistic regression as well. And in order to build the gradient descent, you need this cost function equation. Okay, so the gradient descent works based on the cost function, because it tries to check the cost function value for different weight value and bias value until it finds the optimum weight value and bias value. So this is the importance of cost function, and I hope you are clear up to this point. And if you have any doubts, please mention in the comments. And that's it for this video. I'll see you in the next upload. Thanks for watching.